So right now we are going to understand the envelope results in multivariable optimization. Okay. Now, what are envelope results? These are results in economics which are critical tools often used in optimization problems to determine how the value of an objective function is changing when the parameters change. So, for example, if we have the example of, say, maximizing or minimizing an f having x, which is a variable, and a parameter theta, which is constant. And there are basically multiple constraints. Okay, so there are supposing m constraints. Now, what is the result of this theta changing on the optimal value of f? Okay, that is what we try to understand in this area. Or in simple terms, envelope results helps us to understand the sensitivity of optimal solution to changes in external parameters. So if I want to maximize or minimize this function, I will be getting an optimal value. The optimal value, I call it f star. Okay, I call it f star. So this x star is also a function of the parameter theta. How will this f star change due to changes in theta? Okay, so we aim to basically take a look at that. So in terms of a mathematical formulation, this, supposing I want to maximize this f, okay, and this f is basically the objective function and theta is the parameter. The envelope theorem provides a way to calculate the derivative of the optimal value of the objective function with respect to the parameter theta, okay, without needing to compute the derivatives of the optimal choice x star. So basically, if I were to write it down, so let me write down what this means. It tells us a way to calculate this value, that is del f star del theta. So to say it in words, the envelope theorem provides a way to calculate the derivative of the optimal value of the objective function with respect to the parameter theta without needing to compute the derivatives for the optimal choice, that is x star. Okay. Now, let's prove this. Okay. How many of you want me to prove this? Please type P in the chat box. Okay. चलो ठीक है. Let's go into the proof. चलो proof को start करते हैं. Proof. So this we know that if we want to maximize f with respect to x, first order condition is something that first order condition in order to find out the maximum value x star dependent on theta will be basically del f del x. Here I can say that x star theta del f del x is equal to 0. That's the first order condition that we already know. Now, let's take the value function v theta, which measures nothing but this f. Okay. So basically, we need to find out how v theta changes with theta. how v theta changes with theta. So we basically differentiate v theta by theta, which is equal to, basically, you will get del f del x del x del theta and del f del theta directly. Please understand each of these f has x star. This is for x star. Okay, this one. Now we know for a fact that the first order condition, what did we have? Del f del x is equal to 0. That's the first order condition. So thus, this particular derivative simplifies to, this part is 0. Okay, this is 0. This becomes 0, and this is basically del f okay. Now this is the key result of the envelope theorem, that the objective function's optimal value, the change in that with respect to theta, is simply del f del theta. So there is, this part is called the indirect effect of theta, but this indirect effect does not affect the optimal value, because in the first order condition this becomes 0. When I maximize, my del f del x is becoming 0. So this effect is being nullified. Okay, that is what the envelope theorem says. So if I want to talk about the interpretation, the envelope result tells us that the rate of change of the objective function's optimal value with respect to a parameter theta can be found by directly differentiating the objective function with respect to theta. Okay, so the result is telling us that the rate of change of the objective function's optimal value with the parameter theta is found directly by differentiating the objective function with theta, and it is obviously evaluated at the optimal choice of x star. Okay, this simplifies the analysis significantly. I don't have to worry about the indirect effect of theta affecting my x star and hence affecting my value function. Okay, so this basically simplifies the analysis as it circumvents the need to differentiate the optimal choice. I don't have to differentiate with respect to x at all. Okay, so that is what is the interpretation. If I want to write it down, we can write it down. Okay, give me a moment. Let me type it. So this is what I just shared with you. The envelope results tell us that the rate of change of the objective function's optimal value with respect to the parameter theta can be found by directly differentiating the objective function with respect to theta, evaluated at the optimal x star. Okay, this simplifies the analysis as it circumvents the need to differentiate the optimal choice. Optimal choice क्या है? Optimal choice है x star. मुझे उसको अलग से differentiate करना नहीं पड़ रहा है. So this is what is simplifying the analysis. Okay. Now, if I were to talk about an example, okay, let's consider a simple economic example where a firm is trying to maximize its profit. So the profit is a function of x and p. That is the quantity and the price. Okay. So this is equal to what? revenue minus the cost, obviously. Revenue, I take it as px minus the cost is a function of x only. Okay, where obviously, as I said, p is the price, c is x is the quantity, p is the price, x is the quantity, and cx is nothing but the cost that the firm faces. Okay, now according to the envelope theorem, the effect of a small change in price on the maximum profit can be directly found by differentiating the profit function with respect to p. So according to the envelope theorem, the effect of a small change in price p the effect of a small change in price p on the maximum profit can be found out by simply differentiating the profit function with respect to p. Okay. So basically, what are we doing? We are basically ignoring the effect or ignoring how optimal x star changes with p. Okay. Right. Now, why is this so essential? Why is this tool, that is the envelope theorem, so essential? It is essential in economic theory because, say, when we do comparative static, like in, say, consumer behavior, we do a static that as income changes, what is the effect on the optimal utility? If the prices are changing, what is the effect on the optimal utility? So whenever we do a comparative static, its power lies in simplifying the complex problem into a very simple problem. It is allowing economists to focus on direct parameter effects rather than the indirect effect of it affecting the optimal uh, x. Okay, so I don't have to worry about any indirect effect of the parameter. I only have to think about the direct effect of the parameter. Okay, chalo theek hai. So this is what is the envelope theorem said in brief. Now, it's important for us to not only talk about the envelope theorem in this manner, but we'll also have a Lagrange multiplier method overview for the envelope theorem. Okay, so let's now go into the Lagrange multiplier method. Okay, let's take a look at the Lagrange multiplier method. Okay, let's understand what is the Lagrange multiplier method. So we'll consider the problem that we considered earlier. We'll take maximizing fx theta subject to the constraint. I'll call this gx theta is equal to 0, considering that this g is actually representing multiple constraints. So I'm considering the entire thing in the vector format. So it's very easy for you to, take a look at it. So let's form the Lagrange. So Lagrange is basically fx theta, okay, plus lambda gx theta minus 0. So that's what it is. This is the Lagrange. So let's find out the first order conditions. The first order conditions for optimality derived by finding out the partial derivatives of the Lagrange with respect to x and lambda. These are the first order conditions. So del L del x is equal to 0 will basically give me this is what we'll get. Okay. And with respect to lambda, I'll get okay. Now, to understand how the derivative of the value function relates to the Lagrange multiplier, let's differentiate the value function with respect to theta. Okay. So the value function that we saw earlier was basically fx star. Okay. So it's nothing but maximizing my f subject to the alternative. Okay. So we differentiate the v is basically equal to, again, the same thing. This is what we have. Now, from the first order condition, of the Lagrange, we get this del f del x is equal to okay. Right? And we know the fact that okay. So let's take all this information on the next page. Del f del x that we had here is basically minus lambda del g del x. So this is del x del theta. Now, we know that gx theta is equal to 0. So if I differentiate this, I'll get del g del x del theta plus del g del theta is equal to 0. Okay. So what do I have? I have basically del g del x del theta is equal to minus del g del theta. extremely important result. I call this result A. Put this result A in this expression. So when I put this result A in this expression, what will I ultimately get? I'll get dv d theta is equal to del f del theta minus lambda del g del x del theta is equal to minus del g del theta. So okay, this is what we'll get. Now, obviously, when I apply the Lagrange, where was the Lagrange? The Lagrange was this. So if I go back to my Lagrange, and I differentiate my Lagrange with respect to theta, it's basically del f del theta plus lambda del g del theta. That is what we got here, right? So this is nothing but the Lagrange differentiated with respect to theta. Del f del theta plus lambda del g del theta. That is what we have here, right? So what we get is an amazing result again, that the value function differentiated with theta is equal to the Lagrange differentiated with theta. Okay, it's nothing but equal to the Lagrange differentiated with theta. So dv d theta we first got as del f del theta at the optimal, right? And this is also the same as del lambda del theta at the optimal. Okay, obviously at the optimal means that this means that x is at x star and lambda is also at lambda star. Okay, so x is at x star and lambda is also at lambda star. Now, why did we study this? What is the interpretation of this? The interpretation is this, that this result basically shows us that the derivative of the value function v with respect to the parameter theta can be found simply by taking the partial derivative of the Lagrangian with respect to theta. Okay, and obviously it is evaluated at the optimal values of x and lambda. It effectively combines the direct effect of theta on the objective function f and the indirect effect of the constant g. Okay, so we have taken a look at the envelope result from the point of view of f and as well as from the point of view of Lagrange. Okay, so in summary, the envelope theorem's derivative result aligns with the derivative obtained via the Lagrange multiplier method as well in constraint optimization. Okay, this connection simplifies analysis by allowing us to calculate the sensitivity of the optimal value with respect to changes in the parameters, considering both the objective and the constraint. So this comprehensive understanding of the envelope theorem basically simplifies and makes it easier for you to understand that we don't have to consider the indirect effect at the optimal values, क्योंकि वो first order condition से zero हो रहा था any which ways. Okay, right. So that ends the session for the envelope theorem. We shall be going into more analysis in further videos. Thank you.